So now we want to look at the definition of the expected value of a random variable, and we will see this repeatedly throughout this video. We will make a division. Specifically, namely, we want to define it for a discrete probability distribution and also do the same for a continuous random variable in particular. And that makes a big difference because in the first case, we have a finite number of values. We have a finite number of values that can be achieved and also only a finite number of probabilities. While in the second case, we have continuously many. That means in the first case, we can often work with sums, and in the second case, we have to replace this sum with an integral. This has the consequence that the calculation is often significantly easier for discrete random variables, while for continuous ones, knowledge of antiderivatives and derivatives is necessary. In this video, we will primarily focus on the discrete case, which is the simpler part, but we will also repeatedly address the formula for the continuous case. Let's take a look at this. The random variable, here is the formula, and let's go through it briefly. So we always have a random variable given, and then we call the whole thing the expected value, and often write e of x. And as mentioned, there is this division. Let's take a look at how it looks for discrete random variables. What we are doing here is taking the sum of all the values that the random variable can take and multiplying it by the pi. If you remember, that is the probability that the value xi is taken. Exactly. And we sum that up, and we will also see an example of how it looks. You probably already know the formula. Exactly. So now let's look at what happens when x is a continuous random variable. And then what we always do happens, we replace the pis with the density function. You remember in a continuous random variable, the probability that x has exactly one value is always 0. That means it doesn't make sense to work with that. Rather, what we actually want is the density function. Otherwise, we do the same, so x times f. And then again, essentially, we replace the sum with the integral in this context. It will always be the case that we complement the pi's with the f, that is the small f, and the sum with the integrals. Well, let's take a look at this in the simplest example. Imagine we have the following random experiment. We have a dice roll with a 2001, a die, and our random variable is the number shown on the die. And now we are looking for the expected value, and for that, let's quickly write down the distribution again. You remember in one part you write the values and then you write the probabilities. And the values in this case are 2001, these here. And the probabilities are always 1/6. And now we remember the formula, which was E equals the sum of xi times pi. And that means we write x times p, so that's 1 times 1/6, 2 times 1/6, 3 times 1/6. In this case, always 1/6, because the probability is always the same, 2001. Right here again, 6 divided by 6, and that is the numbers 1, 2, 3, 4, 5, 6 divided by 6, and that is 3, 6, 10, 15, 21 divided by 6, and that is 3.5. Okay. And that is also going in a direction that we would expect, because 3.5 is exactly the mean or the arithmetic mean of the numbers 1, 2, 3, 4, 5, 6. And that makes sense because all probabilities are equal, so the expected value in this case actually gives us the arithmetic mean of all values. Well, but if one probability were different, then there would be a certain weighting. And we can see that in the example when there are 2 dice, and we, for example, form the sum. Okay, good. That was our example. And we also want to think a bit about how this looks for a continuous random variable. An important theorem that will help us, especially with the normal distribution, is that if we have a density function and we have a continuous random variable, the whole thing is symmetric, and a value c, meaning it is axis symmetric, which means f, x, f. That means if we plot this, there is somewhere a line of symmetry, e.g. so. And around this line of symmetry, the whole thing is symmetric. Imagine, we will get to know this again, a normal distribution. Then we can easily read the expected value, namely, it is simply this value c. Exactly, and that means, so to speak, it will allow us later to think about what the expected value of a normal distribution looks like, namely, exactly the peak where the peak is reached. Yes, we will now get to know a few more sentences about the expected value, and we will ask ourselves what happens when we roll 2 dice and look at the sum of the faces. Exactly, that is exactly the current situation we are in now. Let's just think about it a bit. First, we will try to find our omega, and our omega now is composed of all possible variants in its structure. And variants are, so to speak, all possible dice combinations. You can get a 1 and a 1, a 1 and a 2, a 1 and a 3, and you can already see up to 160, then it continues with 2.1 and so on. And in the end, you eventually have 6,6. Okay. And all these variants are equally likely. How many are there? You can think about it. You have 6 possibilities for each die. This results in a total of 6 times 6, so 36 possibilities. And now, at this point in time, we need to take into consideration what the distribution looks like. For this, we will write an psi and a pi here again and consider all possible values that can occur here. And then we can see that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the 12th. And now we are in a different situation. Now we see that the probabilities are not all equal, because we need to consider how many combinations from omega can form a sum of 1. Well, you can see that I have the first one, so 1 obviously does not exist. So the probability is 0, because at least one 1 must be rolled. So, what about the 2? There is one possibility out of 6 and 30, namely the first one. So we have 1, 6, and 30 here. Now we can continue here. What about the 3? And what we see there is that there is, on the one hand, 2001, the 1, 2 as a possibility, but also the 2 first. So there are 2 possibilities out of 6 and 30. And you can do that, and then you will actually see the following pattern. You have 3 out of 6 and 30, 4 out of 6 and 30, 5 out of 6 and 30, 6 out of 6 and 30, and then it goes back down. So in general, 7 has the highest probability, and approximately 1 out of 6, and 30. And now, we need to determine the expected value. Now we have the distribution, and now we determine the expected value. So, what do we need to do? We need to sum, I'll write it down again, pi times psi, which means 1, 6, and 30 times 2,000 plus, 2, 6, and 30 times 3 plus, and so on and so forth. Yes, I'm not going to explain it here. And when you calculate all of that, you will see that the expected value is indeed 7. And that is interesting, as it corresponds to our previous intuition, so to speak. There is also the peak, where the probability is highest, and around it, it is symmetrical. We have already seen in the previous sentence that this is the behavior that is happening here. And we also see something else, namely, what was the expected value with one die? Well, that was 3.5. Now we have two dice, 2001, and suddenly we have 3.5, 3.5. And this leads us to consider the following, namely, can we simply add expected values linearly? And that is indeed correct. The following is the case. If x and y are two random variables, then it holds that e of x plus y equals e of x plus e of y. And that is exactly what happened here. In our example, x would be the sum of die 1, and y would be the sum of die 2. And we know that the expected value of x is 3.5, the expected value of y is also 3.5. So the sum of the dice is 7. And the same applies to EA in this particular scenario. So if A is a factor, i.e. if we roll the dice and then e.g. if we multiply by 3 and then look at the expected value, we can simply pull it out from here. And it is important that you know this formula. We also need it to solve our motivational example. And what is also important is that this always applies, even if the two random variables are dependent on each other. We will also see formulas where it is really about random variables being independent of each other. These formulas always apply and help us, for example. Now, in the example of the double dice roll, to immediately arrive at the value of 7 without this complicated calculation, namely 3.5, so we only need to determine the expected value for a single dice roll. And now we could do the same with 10 dice. And how will that look? We can take the same situation. We take x as die 1 and so on, and x equals die 10, and then we need to calculate the expected value of x, which is nothing other than 10 times 3.5. Yes, and that is, it is approximately equal to 5 and 30. And what is also very important is that they use this formula in these various situations, as well as others. Compare it with this formula. In this case, they are the same. The same result comes out, but it is a different random experiment. The left side is that they have 10 different dice, 2001, and sum everything up. The formula they can use to show this is a different random experiment. They have a die and multiply the result by 10. These are different random experiments. For both, the expected value is, so to speak, 5 and 30. But we will see that in the variance it will not yield the same result. That's why I am already saying that they should be careful to distinguish between these two random experiments. Indeed, exactly, the next sentence is one that talks about the following detailed explanation regarding the product of random variables. So imagine you have two random variables, and now it only applies to independent random variables. Then it is indeed the case that what we expect holds true, namely, that the expected value of the product of the random variables is the product of the expected values. And that is also, so to speak, nice. And again, pay attention, it only applies to independent random variables. We will see this a few more times now, why it is important. And what does that help us? We will again do an example with two dice. And in this case, we will not take the sum of the dice, but rather the product of the faces. And essentially exactly what we are saying is that means the expected value of this thing is... So when we look at die 1 and die 2 with different random variables, we have that the whole thing is 3.5 squared. Or rather, what do we have? 7 times 2. squared, so 49/4. Okay, exactly. So we also do not have to calculate this by hand again. We could do this by writing out all the values that the products can be, then looking at which values have which probabilities, and then using the normal formula, no 1,000. With these calculation laws, we are very, very fast and can solve this task super easily. Yes, that was the input on the topic of expected value. And in the next videos, we will look at the topic of variance, of random variables, what the formula is, and which laws apply here. Take care.